We now start the third module of chapter 7, where we will learn two things mainly. We will first start with the Jordan decomposition theorem, and then we will learn some computational techniques for calculating Jordan canonical basis and the Jordan canonical form. Now, what is Jordan decomposition theorem? It says that a linear operator T on a finite dimensional vector space V can be written as a sum of a diagonalizable operator and a nilpotent operator, assuming of course that the characteristic polynomial of the operator splits in the base field. Now, why do we come to such a theorem? If you look at the Jordan blocks, they are of the form lambda 1 0 lambda, if we take that 2 cross 2 Jordan block, and that can be written as lambda 0 0 lambda plus 0 1 0 0. So, the first one lambda 0 0 lambda, that is a diagonal matrix, but the other one 0 1 0 0, that matrix has the property that if we multiply it twice, then we get the 0 matrix. Such matrices or operators are what are called the nilpotent operators. So, you can see that a Jordan block, at least a 2 cross 2 one, is being written as diagonal plus nilpotent, and this can be extended, and we can see that for a linear operator we can have this expression. Not only that, if we assume that the diagonalizable and the nilpotent operator they commute, then we also have the uniqueness of expression. Let us first start with the Jordan decomposition theorem. Let V be a finite dimensional vector space over a field F. Definition: an operator T from V to V is called nilpotent if T raised to K is the 0 operator for some positive integer K. T raised to K denotes the composition of the operator T K times. Now, the Jordan decomposition theorem, which says that if T is a linear operator on a finite dimensional vector space V such that the characteristic polynomial of T splits in F, then T can be written as S plus Z, where S is a diagonalizable operator, Z is a nilpotent operator, and Sz is equal to Zs. We divide the proof into these steps. First one, suppose that T has only one distinct eigenvalue lambda with multiplicity n, which is dimension of V. Then V is k lambda, the generalized eigenspace. If we take Z is equal to T minus lambda I and S equal to lambda I, then T is equal to Z plus S, and also it is easy to see that Zs is the same as Sz. S is diagonal in every basis and Z is nilpotent for V is k lambda, and that is kernel Z to the power n. Now, the general case, suppose that lambda 1, lambda 2 and so on lambda k are the distinct eigenvalues of T with multiplicities n1, n2 and so on nk. Let Ti denote the operator T restricted to the generalized eigenspace k lambda I. Then T is the direct sum of these operators T1 and so on Tk, and since each Ti has only one eigenvalue lambda I, we can apply the previous result. Therefore, we can write Ti is equal to Si plus Zi such that Si is lambda I, that is diagonal on k lambda I, and Zi is equal to Ti minus Si is nilpotent of order Ni on k lambda I. Then we have T is equal to S plus Z, where S is S1 direct sum etc. Sk, and Z is Z1 direct sum etc. up to Zk. Clearly Sz is equal to Zs. Moreover, Z is nilpotent and S is diagonalizable. Why is that so? If M denotes the maximum of these multiplicities n1 and so on up to nk, then Z raised to M is Z1 raised to M direct sum and so on Zk raised to M, and that is equal to 0, and S is diagonalized by a basis for V which is made up of basis for the generalized eigenspaces, hence the proof. Now we talk about the uniqueness of these operators S and Z. Under the hypothesis of the Jordan decomposition theorem, there is only one way of expressing T as S plus Z, where S is diagonalizable, Z is nilpotent, and Sz is equal to Zs. Proof: let k lambda 1 and so on up to k lambda k be the generalized eigenspaces of T corresponding to the distinct eigenvalues lambda 1 and so on up to lambda k. Then V is k lambda 1 direct sum etc. up to k lambda k, and T is T1 direct sum etc. up to Tk, where Ti is the restriction of the operator T on the generalized eigenspace k lambda I. Note that k lambda I is invariant under every operator that commutes with T. Now, since S and Z both commute with T, therefore, k lambda I is invariant under S and Z. Let us write Si equal to lambda I and Zi is equal to Ti minus Si. It suffices to show that S restricted to k lambda I is Si. For this, Z restricted to k lambda is Zi, proving the uniqueness of S and Z. Since S is diagonalizable, so is S restricted to k lambda I, and therefore, S restricted to k lambda I minus lambda I is S restricted to k lambda I minus Si is also diagonalizable, and this operator is the same as Zi minus Z restricted to k lambda I. Since Z restricted to k lambda I commutes with lambda I and with Ti, it also commutes with Zi, and we can use the binomial theorem to prove that Zi minus Z restricted to k lambda I is nilpotent. Hence, the matrix representation of S restricted to k lambda I minus Si is nilpotent diagonal matrix, and therefore the zero matrix, hence the proof. Let us now learn some computational techniques for calculating the Jordan canonical form. We have to find cycles of generalized eigenvectors, and those cycles would give rise to a Jordan canonical basis. That is what we have seen in one of the theorems. Now, the question is how to choose those cycles. So, first we will start with the operator, find the distinct eigenvalues, and then from eigenvectors we have to see that some of these eigenvectors will be the initial vector of a cycle. We will use a good and effective method of the dot diagram to do this computation. Let us see. By a previous theorem, each generalized eigenspace k lambda I contains an ordered basis Bi consisting of a union of disjoint cycles of generalized eigenvectors corresponding to the eigenvalue lambda I. Then B, which is the union of these Bi's, is a Jordan canonical basis for T. Now, for each I, if Ti denotes the restriction of the operator T on k lambda I, and if Ai denotes the matrix representation of Ti with respect to Bi, then Ai is the Jordan canonical form for the operator Ti, and then when we put these Ai's into the block form, then J, which is the matrix representation of T with respect to B, is the Jordan canonical form for T. Let us now discuss this useful technique of the dot diagram. The dot diagram of Ti means T restricted to k lambda I. Suppose that Bi is a disjoint union of cycles of generalized eigenvectors C1, C2 and so on Cni with length P1, P2 and so on Pni, and P1 is greater than or equal to P2 is greater than or equal to so on greater than or equal to Pni. The dot diagram of Ti contains one dot for each vector in Bi, and the dots are configured according to the following rules. The first rule is that the array consists of Ni columns, where one column is for one cycle. Counting from left to right, the jth column consists of the Pj dots that correspond to the vectors of Cj, starting with the initial vector at the top and continuing down to the end vector. So, you can see this diagram over here. So, this is for each cycle. So, here you have the initial vector and here you have the end vector, and we have exactly Ni columns, one for each cycle, and the rows correspond to the vectors in the cycle, and each cycle has a precise length. So, you can see that in the first column, which represents C1, there will be P1 rows, then in the second column there will be P2 rows and so on. In the nith column there will be Pni rows. The dot diagram of Ti has Ni columns, one for each cycle, and P1 rows, since P1 is greater than or equal to P2 is greater than or equal to and so on greater than or equal to Pni. The columns of the dot diagram either become shorter in length or remain the same in length as we move from left to right. So, these are the rules, and then Ni is equal to dimension of n lambda I. Ri is the number of dots in the ith row given by R1 is equal to dimension of V minus rank of T minus lambda 1 I, and Rj is equal to rank of T minus lambda I raised to j minus 1 minus rank of T minus lambda I raised to j if j is greater than 1. Now, let us understand this method with the help of some concrete examples. To begin with, take A to be this 4 cross 4 matrix given by 2 minus 1 0 1 in the first row, 0 3 minus 1 0 in the second row, 0 1 1 0 in the third row and 0 minus 1 0 3 in the fourth row. Then Pt given by t minus 2 whole cube times t minus 3 is the characteristic polynomial. The distinct eigenvalues are lambda 1 equal to 2 and lambda 2 is equal to 3 with multiplicities 3 and 1 respectively. Therefore, the dimension of the generalized eigenspace k lambda 1 is 3 and dimension of k lambda 2 is 1. Let T1 denote the restriction of T on k lambda 1 and T2 denote the restriction of T on k lambda 2. Now, the dot diagram of T1, it has 3 dots and the possibilities are like this: 1 dot each in 3 columns. Then there are 2 columns, with the first column having 2 rows and the second column having only 1 row, therefore 3 dots in total. And another option is that there is only 1 column and it has 3 rows. So, you can see that in the first case there are 3 cycles and the cycles are of length 1. In the second case there are 2 cycles, the first cycle is of length 2 and the second cycle is of length 1, and in the third case there is only 1 cycle whose length is 3. Let us now calculate this number R1, which is 4 minus rank of A minus 2i, that is 4 minus rank of that matrix 0 minus 1 0 1 0 1 minus 1 0 0 1 minus 1 0 and 0 minus 1 0 1, and then easy computation shows that this number is 4 minus 2 and that is 2. Therefore, the dot diagram would be the one with 2 columns, where the first column has 2 rows and the second column has only 1 row. That is because R1 is 2 and R2 is 1. Therefore, the Jordan canonical form for T1 would be first Jordan block appearing on the top left corner is 2 1 0 2, and then another Jordan block which is a 1 cross 1 matrix 2, and the Jordan canonical form for 3 would be the Jordan block 2 1 0 2 on the top left, followed by the 1 cross 1 block 2 and then the 1 cross 1 block 3. Let us now calculate a Jordan canonical basis for T. We first find a Jordan canonical basis for T1. This is the dot diagram for T1. You can see that we have a cycle T minus 2i V1 and V1, and then there is another cycle of length 1, that is V2. Therefore, V1 belongs to kernel of T minus 2i square, but does not belong to kernel of T minus 2i. Question is how to choose V1. The matrix A minus 2i is this 4 cross 4 matrix given by 0 minus 1 0 1 in the first row, 0 1 minus 1 0 in the second row, 0 1 minus 1 0 in the third row, 0 minus 1 0 1 in the fourth row, and we can also calculate A minus 2i square, which is given by 0 minus 2 1 1 0 0 0 0 0 0 0 0 and then 0 minus 2 1 1. It is not difficult to see that these 3 vectors 1 0 0 0, 0 1 2 0 and 0 1 0 2, they form a basis for kernel of T minus 2i square, which is k lambda 1. Note that these 2 vectors 0 1 2 0 and 0 1 0 2, they do not belong to the eigenspace in lambda 1. So, we choose V1 now to be 0 1 2 0 and consider T minus 2i of V1, which is A minus 2i of V1, and that is minus 1 minus 1 minus 1 minus 1, and choose V2 to be 1 0 0 0. This belongs to n lambda 1 and this is linearly independent of the vector minus 1 minus 1 minus 1 minus 1, and therefore we have this set consisting of the vectors 1 0 0 0, 0 1 2 0 and minus 1 minus 1 minus 1 minus 1, which is linearly independent and hence a basis of k lambda 1, because we know that dimension of k lambda 1 is 3. Therefore, the Jordan canonical basis is B1, which is 1 0 0 0 1 2 0 minus 1 minus 1 minus 1 minus 1, and it's associated to the dot diagram given by this minus 1 minus 1 minus 1 minus 1 is an initial vector, and 0 1 2 0 is a final vector. They form a cycle, and another cycle of length 1 is just the vector 1 0 0 0. Since lambda 2 is equal to 3 has multiplicity 1, we have dimension of k lambda 2 is equal to dimension of n lambda 2 is equal to 1. Hence, any eigenvector constitute a basis B2. Therefore, we may consider B2 is equal to just a singleton 1 0 0 1. Now, we have B, which is the union of those two bases for the generalized eigenspaces, and we have 4 vectors 1 0 0 0 0 1 2 0 minus 1 minus 1 minus 1 minus 1 and 1 0 0 1, and this is the Jordan canonical basis for A. And if we want to write the basis change matrix, then that would be Q, where the columns are precisely filled with those vectors appearing in the basis. Therefore, QJQ inverse is A. Let us look at one more example. Let A denote the matrix given by these 4 rows 2 minus 4 2 2, minus 2 0 1 3, minus 2 minus 2 3 3 and minus 2 minus 6 3 7. The characteristic polynomial is Pt given by t minus 2 whole square into t minus 4 whole square, and the eigenvalues are lambda 1 equal to 2 and lambda 2 equal to 4. Let T1 denote t restricted to k lambda 1 and T2 denote t restricted to k lambda 2. Again, let us write the dot diagrams. Dot diagram of T1. So, there are these two possibilities. One is having 2 1 cycles, another is having 1 2 cycle. Now, let us calculate these numbers R1, which is 4 minus rank of A minus 2i, that is 4 minus 2, that is 2. Therefore, the correct dot diagram is 2 1 cycles, and that is what you see over there. Hence, A1, which is the matrix representation of T1 with respect to the basis B1, has to be 2 0 0 2. In this case, B1 is any basis of n lambda 1. For example, this set consisting of these two vectors 2 1 0 2 and 0 1 2 0. And the dot diagram of T2, we have R1 is 4 minus rank of A minus 4i, that is 4 minus 3, that is 1. Therefore, the correct dot diagram is 1 2 cycle, and the Jordan block A2, that is the matrix representation of the operator T2 with respect to the basis B2, is this Jordan block 4 1 0 4, where B2 is any basis for k lambda 2 corresponding to the dots. In this case, B2 is a cycle of length 2. The n vector of this cycle is a vector V in k lambda 2, which is kernel of t minus 4i square, and we must satisfy the property that V is not in n lambda 1, that is kernel of t minus 4i. Now, it is easy to see that a basis for n lambda 1 is this singleton 0 1 1 1. Now, choose V to be any solution of A minus 4i x is equal to 0 1 1 1. For example, V is equal to 1 minus 1 minus 1 0 would do. Then B2 is A minus 4i V comma V, and that is this set consisting of the vectors 0 1 1 1 and 1 minus 1 minus 1 0. Hence, B, which is B1 union B2, is this set consisting of 4 vectors given by 2 1 0 2, 0 1 2 0, 0 1 1 1, 1 minus 1 minus 1 0, and that is a Jordan canonical basis for A. And the corresponding Jordan canonical form is given by these two blocks A1 and A2, where A1 is this diagonal matrix 2 0 0 2 and A2 is this Jordan block 4 1 0 4. We have learnt theorems about Jordan canonical form and also some techniques to compute a Jordan canonical form and a Jordan canonical basis for a linear operator on a finite dimensional vector space. But a condition on the operator which we cannot do without is that about splitting off the characteristic polynomial in the base field. Now, if we ask what happens when the characteristic polynomial of the operator does not split in the base field, that means some of the eigenvalues are not in the base field, but in some extension of the base field. Can we talk about a good canonical form for the operator? It so happens that we can, but after some preparation, we will see that we require a more generalized concept of a vector space called modules, which we will learn in the next chapter.